All right, so I think we are ready to go. So good afternoon, everyone. It's a great pleasure to have you here again this week. And this week we have a very special guest, Mr. Florian Busch. He is an architect and he is a heavy user of technology. So he studied architecture in different countries, Germany, UK, and he has his own architecture office here in Tokyo, and he made some really interesting constructions. And in addition to all that, he's a friend of mine, so I have the pleasure of meeting him every Saturday, and we talk a lot about the interplay between nature and architecture and mathematics and biology. So every time we talk, these conversations really open up my mind. So I thought that it would be very nice for him to have a talk for us, so it can also open your mind. That the way that they use technology at his office is really fascinating. So it's a great pleasure to have Florian with us today. And yeah, I think that's it. So Florian, thank you very much for joining, for accepting the invitation. I know you're very busy. So it's a great pleasure to have you here today. And with all that said, I think, the stage is all yours. And yeah, that's it. I will hide myself from now. Thank you.
Thank you very much, Tiago. Hello, everybody. I'm nicely nervous for two reasons, mostly. One is that I hardly get a chance to talk to an audience like yourselves from a different field, and having talked to what Tiago just mentioned, having had the opportunity to talk to him very often, it also gives me a little bit of an insight of what I think at least some of you might be doing. And the other reason is that I, as probably everybody knows, with the pandemic, these Zoom lectures, so being completely stripped of the opportunity to connect with you in the same room as would be normally the case, it's a very weird situation, and you'll just have to bear with me. I shall try to start my screen, share my screen, and you should be seeing an old TV thing, and we'll just go. Now, my company is called Florian Busch Architects, and I've been in Tokyo now for almost 19 years. My own office, we have been going for about 12 years now. In this lecture, I will just go out on a limb and shamelessly expose my lack of knowledge to you in a field that your knowledge is far superior to mine, but with the purpose to weave threads of thought together. And if in the end we will have again together arrived at a small network of connections, I think we or in this case I shall have succeeded at something, and I really look forward to hopefully a discussion. Computational design is about 30 plus some years old, and if we include computational means without the computer, we will see in this lecture much older than that. And architects are trained to be problem solvers. We are really problem solvers par excellence. Looking at something from many angles. So it's often said that architects are good at many things, but experts at none. And that's probably very true. What I want to do, and as the title says, from form to formation, I want to first provide a common basis of what we need to get an understanding of what architecture is, and then move on to, within that definition, to see how we as architects work on architectural processes. Just as we now extend our capabilities, our perceptive capabilities, for example, with the Webb telescope, with the Webb Space Telescope, to use infrared, etc., to open up worlds that were completely unknowable to us. I understand, or I feel, that computational means are an extension to our very limited brains, and that's how we use the computer in the architectural design process, not as a drawing tool, which it is of course used also, but as what I think is much more interesting, as an analytical tool and a generative tool. Biology has become indispensable for architecture, but architecture has also become indispensable for biology. Frei Otto said that in 1971, so a little over 50 years ago. And I think these two sentences are actually quite easy when we have some images, but they're very important to understand what we are trying to do. So what is architecture? Which of course we will not be able to answer in 1 hour or even in a day or two, or a longer time. It's a highly complex question, but maybe we get a little bit of an idea what in this context is architecture. It's a little bit like Uexküll's, Johann Uexküll, which I'm sure you are very familiar with, who coined the term of Umwelt, which is German for around world, or which is now translated as environment. He said that an organism is basically a network of relationships that determine their specific reality. Again, let's keep those sentences. Biology has become indispensable for architecture. Architecture has also become indispensable for biology in mind. And just looking at these images of a stone, of a coral, of a wasp's nest, or of the architecture of soap bubbles. And you may have, you may be beginning to spot the tendency here. The title was kind of a spoiler, formation, from form to formation. The processes of formation in these 4 instances that we just looked at are becoming quicker and quicker. Stone takes a long time, coral, wasp nest, soap bubbles are forming. We can for us humans, we can observe them live. And what they all share is this aspect of time. And that is something that the conventional, let's say, conception of architecture usually does not understand or does not include. People look at architecture as an object. It's a house, it's a building, it's a church, it's a museum. That kind of very limited conception of architecture is something that we have to leave, this baggage we have to leave behind us and look at these processes. Julian Vincent, a zoologist from the UK, coined this famous sentence, for a hedgehog, shape is cheap, but material is expensive. So for nature, shape is cheap, and material is expensive. And unfortunately for the construction industry, it has been the opposite, especially now material is still expensive, but shape is so much more expensive. In order, rather than follow with learning from the material or follow what the material forces can do, architects, construction industry are very often forcing materials into a shape, which of course is 99% of the case straight lines, yeah? Rather than understanding the potential of the material. Frei Otto, whom I quoted, was the director of the Institute for Lightweight Structures at the University of Stuttgart. And this is just a short movie clip of promotional video of what they were doing at the time. So this is before computational design per computer is a thing. That's the 1970s. And this is more like a physical computation of shapes, in this case using soap, to see how nature in real time creates minimal surfaces. Extremely fascinating, extremely powerful and revolutionary, and the consequences we can still feel today. So Frei Otto was a forerunner of structural engineering, of structural things that are still relevant today. As you can see, the soap with no effort computes the form through formation. And Frei Otto is famous for the Olympic Stadium in Munich, for the Olympic Games in 1972, which is often seen, and I'm one of those proponents, as one of the best examples of post-war Germany. You have to juxtapose this kind of structure to what the Nazis did in 1936 in the Berlin Olympics, where the idea of humans who dictate as absolute rulers and who impose their limited thinking on something, in this case even on the human, or especially in Nazi time on the human beings, but it goes back to the absolutism, from compared to nature, hilarious hubris. And then takes that to a completely different and shows an open society in post-war Germany in this kind of structure. Absolutely fantastic. And again, architecture is a process, as you can see, and this is based on very, very simple rules. And a lesser building very close to the Olympic Stadium is also in Munich, is at the zoo. That's an aviary at the Hellerbrunn Zoo, which I would think is purer, is less, there's less compromise in the structural integrity of that. A beautiful, beautiful structure. Well, funny that this bird is actually flying outside, but the birds that are confined inside have about 5,000 square meters of area with a very, very limited amount of material. So Frei Otto's thinking was often, or Frei Otto's method was often called thinking in models. They built these models, they used very unconventional methods. Let's go back even further to the 1880s. Antoni Gaudí, which is probably more famous among non-architects. The Sagrada Familia, as you can see, the model on the top. And what's really interesting is how he 140 years ago computed these kind of forms. And basically it's sandbags and letting gravity find the ideal catenaries to minimize the structural effort, yeah? And then you flip it and you have the Sagrada Familia. Mark Burry, an Australian engineer, is or has been in charge of finishing the Sagrada Familia. I mean, it's supposed to be, I think, supposed to be finishing in a couple of years, a few years. And he said that it's still, I mean, I met him, like, I think in 2005, that it is cutting edge. And it was, at the time, it was pushing the limits of what computers can do to calculate the exact form of all the different stones, how they need to be cut in 3D to fit into that church. A contemporary of Gaudi, Darcy Thompson, in his seminal book on growth and form, studies as a biologist the morphogenesis, in other words, the process of formation of patterns and structures. And now I'm jumping again, like, to the contemporary of Frei Otto, David Raup, a paleontologist who studied, among other things, shells, helicoids, and made this amazing study of how they are formed. They are, well, the first parameter, which we don't see here, is actually the shape of the generating curve of those. And then the d, the distance that you get is from the axis is the d. And then we have the w, which is kind of the expansion rate, yeah, expressing how much of the tube's diameter increases as it spirals. And T is the translation. So yeah, how much does the tube actually move vertical? So if T is horizontal, then how much does it go up? And then he made this amazing space of possibilities of, you know, any helicoid, calculated any helicoid that is actually possible, and then mapped in this space of possibilities what actually exists, or what has been found to exist in nature. And you can see in this hatched area, it's a relatively small part, and then there's these mathematical possibilities which nature has not yet explored, or we have not found them. Jump a little bit. This is something I did in the very early days, 2008-9, as I was opening my own office, which is, yeah, in all its humble compared to the shell, the helicoid complexity, it's an attempt at doing something like that, where you have these parameters, and you can see on the very let me try to, yeah, you can see on the very left here, these are, for example, a set of curves, and in this case, they will be straight. Here, they're slightly similar to this first parameter of David Raup, and then you go into this direction, let them rotate, rather than expanding this algorithm, let them rotate and come out in all of these kind of potential spaces. Obviously, yeah, architecturally speaking, or for certain use patterns, some of them or most of them completely useless. But what you're doing is you're generating a set of potential spaces that are capable of far more than you could have preconceived. And then you can make selection and restart the algorithm to move forward. So kind of, let's go a step back towards these helicoids on the bottom, or catenoids on the top, and the mathematical pure optimum And then when it becomes really interesting as humans, I think, is when it gets dirty, when the actual context, the necessity of the context kicks in, and you are moving away from the mathematically perfect geometry to sort of an exactitude of topology, where it's completely exact in itself, but can respond to the actual context. This is a project that I worked on when I was working with Toyo Ito, and it's an opera house that has been completed now. It's a project for an opera house, as you can see, at the time of the competition, and where we used a very, very simple set of rules to start it with as a thought experiment, so to speak, dividing this in a checkerboard and connecting it. And now you can maybe connect the dots of the Frei Otto introduction, all these and kind of a pure mathematical minimal surface that you get with a membrane. And then if you start to actually stitch two more together, you end up with these kind of completely separated by this membrane, separated but continuous spaces, so pink and white. And if you look at it in plan, it's very, again, simple, but then the necessity to respond to context, in this case, program, the urban context, the functions, the program, it's an opera house with larger spaces, smaller spaces, and so on. And you kind of see how the form is not something we could have preconceived, but it is a result of a long process of formation. The digital help, the computational powers, are extremely necessary. It would not be possible. I think this would even not be possible with Gaudi's methods. But it is through something that we humans can kind of get a grasp of, which is on the left, which is somewhere around 400 to 500 control points for this entire structure, which, by the way, is about 22,000 square meters of surface area that you're looking at of this structure. And then let the algorithms behind the hood in real time smooth that out. Yeah? So you're looking at a smooth surface. And so the eventual outcome is responding to structural input, to acoustic engineering input, to building environment, building physics input, and also to, very important, to input from construction. How do you actually build this kind of feedback? And just one of them is a crash testing, again, just to show you the potential of what computers do. This is an earthquake simulation. The building has to be designed as it is in Taiwan to withstand a maximum credible earthquake that could happen every 2,500 years in Taiwan, which is quite a big one. And in this case, it would, of course, that's the crash test where it goes beyond repairability, but you would still be able to, to evacuate. And that's construction site as it was in 2014 of the Grand Theater. Now, this is just a screenshot of what is behind, what's going on in the computer, and the project is really constantly developing in a web of relations. And you can literally draw, or have the computer actually draw a diagram of anything, of any project that we are doing. And if you zoom in there, you would see the different nodes, what they are. Yeah, so this material, or this is this geometry, and so on, and how they relate in the entirety of the project. So the project develops not in terms of matter and form, but through continuous variation of material forces. And I think this is key to understand, and hopefully you remember the two sentences which started this talk. Yeah, so biology and the relationship between geology and architecture. I want to run to just a couple of examples that we have been developing over the years. This is already 10 years old, was a project that unfortunately was not realized. A luxury condominium in the tropics with the task or the project brief to build something that is not the ubiquitous conventional high-rise tower, but to keep it as low as possible, but still have 500 and so units. So we're talking about, I think 100,000 or so square meters of space in total, with all the amenities of condominiums. So the way we approached it was, in the tropics, to the main issue, and this is how people in the past have been living there comfortably, is the relationship with the sun. Because sun is of course necessary for our metabolism and life, but it also is too much is painful, and that's why we looked at the examples of those beautiful trees and analyzed them. What their main benefit is kind of the capacity to self-shade, and so that the tree itself provides shading, but it also has a very clever mechanism to shade. And we were trying to translate that into an architecture that could behave in an analogous way. So instead of having the conventional high-rise tower, we first of all turned it 90 degrees, so it's on the ground, and we started to not have a wall, which it would be, but to kind of let it branch out, and then kind of let it start to build on top of each other to provide areas where, no matter where you are in the building, no matter on what balcony or what terrace you are in this building, you always have a certain amount of hours of shading, and that was the key to this process. And incidentally, it's of course learning from what people have been doing, the vernacular architecture for hundreds, if not longer, years in the East Tropics. So we made the building very, very narrow. It's only about the maximum, I think it was 14, mostly 12 meters. So every apartment in there, every unit could have cross ventilation, and work together with the engineers at Arup to really think this through, to not understand the building as an object, but as almost like a plant, as an organism where all parts work together. And I mean, this is absolutely no longer cutting edge. This is what you do with almost any project right now, no matter how small or big. We analyze it for solar penetration. We analyze it for wind. So in this project, very important that we would have enough wind for breezes, but not too much, and to get the right amount of what is considered a comfortable space without air conditioning. And of course, structural. How can we lighten the structure, even though it would have been a concrete structure, but to make it as porous as possible and still be able to, within that porosity, to have the forces find their own ways to be carried down. And that was the idea of the outcome. So you can see that instead of having 50 stories, we have 15, 5, 5, 5, and we have very complex, but in a way consistent project. Let's go back 7 years later. This is a project that is in Jeddah in Saudi Arabia originally, but over the years, over the months and years, kind of expanded to become a potential project that could respond to many places in the world. And this is it's called the IBDA terminal, which is not really a terminal for an airport. It's a terminal for people, for young entrepreneurs, artists, researchers to come together and have spaces where they can, open their own studios, their own offices, but also benefit from a vast amount of infrastructure for the creative process. And so the client was very into the idea of having a ring. And we, of course, first thing was we studied something else just to prove whether or not a ring is really feasible for this idea. And then we came up with a ring is actually doable, but rather than this generic ring, which you can see, hashtag Apple. I think it was clear from the beginning that if this ring can, through a process of formation during design process for a specific location, but more importantly then through formation to respond to many more places in on the globe, create an environment that is far superior and can respond very subtly to changes. So again, here, this is a radiation analysis of how many kilowatt hours per square meter you would have, and how you want to respond to that. And with a ring, you have good sides and bad sides. So we need to kind of start cutting along the different levels. There are 4 levels in total. And again, these are the same engineers, great engineers from Europe, who, together with us, look at the building as an organism where everything starts to work together. And this is just an idea, but how could a facade react? So we need something that can open and close, like the petals of a plant. But it has to be, if it's built in many places, where construction technology may not so be advanced, it has to be very primitive elements. And so we chose these kind of primitive louvers. You have those louvers, and there's a couple of thousand of them, and all they can do is rotate, open and close. And so when the sun is shining in, they would close, or close to an angle where they can still be indirect light, and when the sun is gone in the afternoon, they open and let in the light, and so on. So the building kind of breathes during the day, and those overhangs that you see around the building, they also provide already an initial state of maximum shadowing where possible. So again, the building behaves in relationships as a network, so to avoid material, to avoid cooling cost or heating cost for that matter, if it's built somewhere else, and at the same time is trying to provide an ideal environment for the people who use it. That's the purpose of doing this. So if you think about a research, or in this case, an institution where a lot of people come together, the main, the driving, or let's say the most important part of the creative process is when people bump into each other, and mostly when these are accidental encounters. So we provided the most amount possible of public space, which you can see at the top in these wide areas. These kind of wide areas that there's a public loop all over, always in the inner place, which is like a garden area, and we really want for people to almost be forced to meet people that they have not necessarily met before, or they wouldn't meet otherwise. In section, as a plan view of this, you can kind of start to understand the scale. It's quite a big building. It's very generous spatially, and this garden in the middle is, of course, almost like an oasis situation where we have a different climate, which again, also through in engineering prowess, we're kind of sucking in the air, which is slightly cooler than it would be on the outsides, which uses the vegetation that you could find in Jinda in this case, and here we can have vegetation that would not grow on the more arid outsides, but here there's more humidity in the inside, and it kind of enhances the climate of the building as the air is sucked in and spread into these cool voids, and led to minimize the amount of energy that is needed to cool the building or have climate control in the building. And these are just jumping through the floor plans, and there's a vast amount of program, different kinds of program, and but let's just look at the structural aspect again to see how computational means are, in this case, structural algorithms are helping us to not only make it realizable, but also to make it feasible for many parts in the world where construction technology greatly varies. So we are looking at, in this case, for a structural algorithm. Again, this is developed with our Arabs team to have the minimal material effort, as you could see in birds' wings, for example, and at the same time we are kind of making it buildable and affordable. I mean, to build something like this in this is extremely would be extremely difficult and not affordable. Build something like this is much easier. And if the program can also, all the program that needs to go in there, all the functions need to go in there, they can be, these kind of structures in the middle can afford them, then that's absolutely the best outcome. So, so this is a mix of structural algorithm and the actual structural algorithm. And as you can see, these openings, there's kind of a feedback process between openings that we need and openings that are possible. And once they're in there, then the structural forces, which you can see as literally a force diagram, they start to find new routes. So there's several iterations, that go through that. And that's kind of there in this structure. There are 80 of those structural walls, and you can see the structural diagram on the left and the actual the way it would be built on the right. Yeah, and that's kind of on the outside how it would look, and from the inside looking into the outside, and see how. What kind of, there's some of the program that's in there, different types of auditorium, music, event hall, etc., etc. That's the library. Yeah. And that's looking from the library into the inner garden. And at the very far, you can see in the high horizon, you can see the city high-rise buildings in the distance. And so let's jump a little bit to a completely different approach, or use case of how we apply algorithms, computer technology, computational means in our design process. This is literally what it says, landing on a small island. It's actually a group of islands in the Philippines, and the client needs to build an airstrip, because there's very high currents. It's very difficult to access this group of islands, and one of them, he wants to have an airstrip to land planes. And so the first thing is that we are actually using drone technology to generate a point cloud of this island. And as you can see, this is 4.9 billion points, which kind of is the limit at the computational powers that we have at the office. But we can reduce it, and then we start to introduce, which is likely a problem of the machine learning algorithm here, to start to introduce some areas where the computer tries to interpolate these black areas that you can see, but it's still at a resolution that is sufficient for our means, because what we want to do is we want to have an airstrip of a length of 1,200 meters to land, and more difficult to take off a certain range of planes. And it should have 60 meters, and the maximum gradient that you can have for airstrips is 2%. But the goals are, I mean, you can probably measure the island and say, okay, 1,200, let's go. But if you have the means to analyze that with what we have here, we can set the goals to have a minimum amount of soil that needs to be moved to not only mostly to save costs, but also to save as much as possible of the island, of course. And the minimum difference is cut versus fill. So you want to ideally just use a couple of bulldozers and put the soil over from where there's too much to where there's not enough, and then that's it. And basing it's on a geometry of a 5 meter resolution, which is enough for this purpose. We can of course go down to make it more accurate, but that's kind of the measure how it would look, how it looks in 5 meter resolution. And then if you go 1 meter, it's you can see that again these areas in the middle here that you can see they are interpolated, where there's the machine learning had difficulties with the differentiating between all the palm trees because they look too similar. But again, these get the scale of the island. You get this pink is kind of the airstrip, 1,200 meters, and the prevailing winds are unfortunately in a direction that we cannot have at 1,200 meter, but we can try to be as close to that direction as possible. And that's kind of how we set up the algorithm. And this is using a parametric software where we can have a evolutionary solver, like a genetic algorithm to find the optimum under these conditions. So we have an initial population of 200, as you can see in this left rectangle, with the white are the ones that are going to be selected after the first generation, and the red ones are those that will be eliminated. And every following generation has 40 offspring, and we have, in this case, we have 4 parameters. This pink area can move in XY. It can, it can rotate in XY. It can move in X. It can move in Y, and it can adjust the gradient within the boundaries that we set, so plus minus 2%. And the field of parameters is what I just explained. Is after the first generation, you can see that the algorithm tries any of the possibilities within that of those or some of them are completely, sometimes even it's moving the airstrip outside of the island partially, and then but it corrects the mistakes. Yeah? And this is kind of the active genome ranking. So you have the best numbers on the top and how these parameters are at this certain state. And if you let this run, yeah, you can see that after first generation, you can see how the algorithm finds a tendency. Yeah? So this graph is where those parameters are approaching an optimum. And instead of, I think we had in the beginning a difference of 150,000, after only 8 generations, we are at 4 cubic meters difference, and this total soil movement is at 200,000 cubic meters, which I would assume that we are very, very close to the ideal, even if we let this run for days. And that's kind of the way this works. So we have the possibility of an n-dimensional space of possibilities to search from and optimize, and it's an extremely powerful tool that is at our hands. And just to give you another quick insight, again, something that you may not expect of architects to do. It's a mountain retreat somewhere in Colorado, and the clients want to study the feasibility for a ski development. So we are using the topography at the best resolution that we have. In this case, we have a LiDAR scan of this area, which is up to, I think, up to 20 centimeters precision, or even better, which is an overkill for this study. We're using an interpolation of, I think, 1 or 2 meter mesh resolution, and then we are doing, kind of really let the computer analyze through the software, for example, all the gradients, where can you ski, where are they live, but also this is something, this is plant health, which is of course crucial because we want to keep as much of the trees as possible, as much of the healthy trees as possible, and to consider where is going to be our intervention, and we want to keep a minimum, keep the intervention to a minimum. We have algorithms and to have annual sunlight analysis, again, to find the ideal orientations, to find the ideal locations, and if you superimpose that with the trees that we are going to keep and so on, to get strategies where we would like to place potential buildings, and also maybe this is just a section through the site, looking at both sides, just to give you an idea how architects are understanding, in this case, a fairly big part of our planet, not as kind of a canvas where we can paint on, but as an organism that we want to engage with, and we want to respond to, and we want to minimize our impact on. If you start to build something here, this is some a quick algorithm that we created to give us an idea of, from any point on the site, we can analyze the maximum views in theory. This is only taking the topography into consideration, so it's not talking about the vegetation or that is actually there, so that would have to be another layer, but you get the idea of what we can do in almost no time now, which would have been impossible in the past. And that's something maybe as a little bit of a funny part, is just to see how it's also something we created to how what is actually skiable. And if I have 2 potential lifts here, green being the base and white being the top of the lift, and how much can I reach with this kind of ski lift. So again, the idea is to, instead of having 30 lifts for a ski area, maybe we only need 5, and we can save valuable resources, and again have minimum impact on the surroundings. So what this algorithm does, it just has a parameter that says anything larger than 5% is skiable, which is pretty slow, but let's say it's still possible without having to push. And then I can, in theory, reach this white area here. So we have a huge area. It's just, if you compare this to other ski resorts, it's amazing. And we analyze the areas of difficulty, etc., and then kind of started to think about a web that would minimize, where others would have put in about 30 to 40 even lifts. We are thinking that we can do with 12. So I'm almost done, and I want to just go back and what is the problem? What are we talking about? And the problem is huge. The problem is that the construction industry built, let's say, not the construction, the built environment in the widest sense, is using about 50% of all the energy consumption of the world. It's responsible for about 50% of all the energy consumption of the world. And the problem is really that the construction industry and architects are a part of that problem, is very, very sluggish and is not capable of using, or not yet capable, or not willing to use the computational powers that are at our hands and are getting stronger every day to be smarter, to be more effortless, to think about those issues, these points that Frei Otto so succinctly showed, which is lightness, and this elegance that is observed in nature. So the outlook is surprisingly, we're surprisingly well equipped to tackle the future. And there are many institutions in the world, and universities, other research institutions, architects who are using these powers and are getting a lot out of it. And just to stay, I thought it would be nice. We started with Frei Otto in Stuttgart, at the University of Stuttgart, and there's currently an extremely bright figure, again, the director of this of another institute. His name is Achim Menges, and he's heading the Institute for Computational Design and Construction. And they are in collaboration with other institutes, with biology research institutes, with other universities. They are doing cutting edge stuff, emphasizing the materiality and how what I said in the beginning, material is not something that we work despite of or against, but trying to understand what the material can do, how the performance of the material, and make use of that. And they are having some extremely interesting projects, and it's definitely worth checking out. And unfortunately, and that's again due to the construction industry, that it's a very sluggish. Of course, there's a lot of safety issues as well, but it's a very slow process to get something to the level of large buildings. I mean, they are doing these beautiful and extremely intelligent, lightweight, effortless pavilions. but I hope, and I hope that, you know, my humble efforts will also lead me into that direction, that we will be part into creating a better future where we are making much more clever use of what's around it and the nature that we are part of. And so since we are in Japan, I think, yeah, we are now still in this kind of idea of the corset, that, you know, we have an ideal of what a shape should look like, and we create this kind of strange corset. But the more elegant way would probably be to act like a kimono, that, you know, it's from katachi to keisei, or from form to formation. And I think that should be the goal of all our efforts. Yeah. Thank you very much.
Great. I mean, it's really, really fascinating, these concepts. I mean, there are so many things that I believe we could borrow, you know, from architecture. For example, I work with protein structures, and, you know, this knowledge to optimize the shape and the use of materials. I mean, it's something that we definitely could borrow, you know, for protein engineering. This is kind of the things that I'm working on, because, I mean, it's the scales are different. Like, we're working in the micro or sometimes the nanometers. But many concepts that you showed, like the tension and the use of materials and to optimize something and to prioritize others, are really close by. So I'm really fascinated to watch these things. So with that said, I think we are ready for a few questions from the participants. I mean, if the participants want, they can ask directly, you know, to Florian, or they can send me in the chat box, and then I ask. It's up to you. So from the folks from the audience, does anybody have any questions for Florian? Okay, I think I just got one here that I wrote. Okay, so someone sent me. So the question here that I received is, in the models that you optimized, so how many variables did you optimize? I think you showed one that you had 4 variables that you wanted to optimize. Is that correct?
That's correct. I mean, it really depends. So I said n-dimensional space, yeah, which is quite nice for architects to talk about, because, you know, we're usually the 3-dimensional people. But it is absolutely feasible to have as many as you need. And the key is, I think, the parameters that you feed, and what's the optimization goal? Because a lot of times we have more than one goal, and how do we weight that? So what we usually do is we just use very simple mathematical formulas to give one goal more importance, to give the weight a higher weight to that, or reduce another, etc. But in theory, we can, there's no, I mean, the computational powers are the limit. Let's put it that way.
Okay, one question that I have is, you know, as you said, we humans have a very close, very intimate relationship to nature, like the amount of sun, the luminosity, kind of the plants that surround us. You know, they can have an effect on the microbial population that lives inside our bodies. So I was wondering here, if one of the variables that the models could optimize is health, like to optimize or to improve the health of the people who spend time inside that building. For example, if it's a workplace, we spend, 8 hours every day inside that building. Or if it's our homes, you know, so is it possible to also take into account the mental and physical health as a variable to optimize when you design the architecture of a new building?
I mean, that's a very good question, and I think that should be at the beginning of anything that we architects do. I mean, if you put it the other way, can we design a building where somebody ends up committing suicide? I mean, that's, you know, if you go down the sinister way. But of course, these are very important parameters. And there was actually the movement of the 1920s, the Bauhaus, you know, light is a huge part of that. And yeah, modernism introduces light. We have to think about the historical context where people lived in these very dark, small window, thick wall kind of environments. And the next point is sanitation. So bathrooms got a huge boost at that time, because it's, again, think about you had shared bathrooms maybe on one floor for 5 apartments or something, and shower was not thinkable. And all of a sudden, that is at the beginning of the 20th century when that kicks in. Now, that's the very, which I completely love to think about. How are we, as you say, we are 8 hours in your office, but you have no window, right? For example, how can that be? Or if there's a window, people put the shelves in front of it. Is it really good? Or what? Something has gone really, really strange. When we kind of, there's an air conditioning, but we could. Even in a place like Tokyo, 6-7 months or maybe longer of the year, you can open your windows and it's the best environment that you can have. But people are just used to closing everything, hermetically seal it, and depend on an air conditioning, which probably needs more cleaning, or you get stuff that you don't even are aware of. So I think it is, and it should be, one of the most important parts when you start any project, and it's also an important part of the architectural profession to be able to listen, to not have a preconceived idea of what a house is, or what in your case what a research institute should be, but you have to listen to so many things, and you have to get as much information, as much data as possible to come up with ideas that are responding to those needs.
Right. I see. So I think we have time for one last question. Anybody wants to ask? Okay, I received one here on the chat. I think it's a more technical question. So the question is, when you optimize for more than one variable, like I think you said, you had many variables to optimize, in the end, the model, I mean, you get more than one good solution, right? So you get more than one good solution, one that is better for this variable, another one that is better for that variable. So the question is, how do you select, like from the kind of optimal solutions that you have, how do you choose the final one to build?
Also a very, very good question, and something that really is part of many discussions among architects or in the architectural field, because the architecture profession has moved from, for a lot of architects or people who study architecture, want to become architects, has moved from the creator, I have this idea and let's build this, to more like a how should I say, a conductor or somebody. As you say, the selection process is extremely difficult and important. But having said that, instead of having maybe 2 or 3 solutions that I could have thought of, that I could have, my brain was capable of thinking of, would have been, now I have 1,000 or more if I want to, right? And I have tendencies. So I think that's really important to acknowledge tendencies, and not to also, another thing, to not understand the process of start and end, but as start interim results. Yeah, let's forget about this and this. This is and new start, and then we kind of you get more and more and more, but you kind of can steer the tendencies. But at the end, if I have, for example, in the maybe the island example is not really good because I think the aesthetic input is not really important if the landing strip is like this or this. Yeah, but we can then have different weights. We can say, okay, this one would be let's say 100 cubic meters less, but the orientation is for the other one, which has 100 cubic meter more soil movement, is better to the wind. And shouldn't we invest? Yeah, shouldn't we pay for those 100 because it's going to be easier to land and take off, for example. So these are things that you can make. Again, in that case, you can increase the weighting of the landing orientation. But I think maybe your question is going into that direction. So if we have, let's say, this one looks quite nice, and this looks quite nice, and this looks quite nice, and they all have very similar. The goal is very. We have the parameters, and the outcome is very, very similar. Which one do we pick? And there are. Sometimes there are sleepless nights. There are thinking but you kind of treat all of them in a maybe it's at the end there might be a gut feeling situation where they're all pretty good and have pretty almost the same results, and then you pick this one, and that's kind of why it is your piece of architecture and not somebody else's.
All right, great. I mean, I think we are running a little bit over time. So with all that, I really want to thank Florian once more for the great presentation and for answering the questions. Thanks for the examples. They are indeed very interesting. So if somebody has any questions later, is it okay if they contact you?
Sure, yeah, sure.
Yeah, okay, great. Then folks.
Sure, and, looking forward.
Okay, so Florian, thank you very much. And everybody, thanks once more for attending. The video will be available next week in our library. I'll send the address to everyone. So thank you very much. Have a good evening, everyone. Bye-bye.
Thank you. Thank you. Bye-bye.